Hey guys, Math 1700. This week we're going to get into exponential and logarithmic functions, which is really cool stuff. Um, well, I don't know about cool stuff, but it's stuff. Um, all right. What I like to do, I mean, the name of your textbook, I forget exactly. It's like business, life science, no, business economics, life and social sciences, or something like that. But because of the nature of this course, in that mostly business majors take this course, I like to focus on the business applications the most. And there are two relationships that we run into, and one of them is this relationship, which says that the ending balance, so get used to A being ending balance, can be calculated by taking the beginning balance times the quantity of 1 plus r. Should be pretty clear what r is. And times t, time in years. Now, guys, this is what is called a linear function. And they are probably the easiest to deal with, but in business applications, they are sometimes the least exciting. For example, if you go invest your money for an IRA, you don't want to get a linear function or a return that's modeled by a linear function. You want to get an exponential function. But anyway, let's serve this as the base. So if you would invest, let's say $10,000, and your rate is 3%, and your time is 6 months, then you could very easily calculate. Let me get this where you guys can see it. That would probably be kind of cool, wouldn't it? You could calculate your ending balance by taking A times P times 1 plus your rate, which never do math with the percentage. Always convert to a decimal. T is always in years. Well, the T we have here is months, so we know 6 months is 1/2 of a year. So guys, we could very easily use our calculator and I'll show you how we're doing this. 10,000 times 1 plus 0.03 times 0.5, and we would see we get $10,150. So the interest on this would be $150. Okay, so that's an example of a linear function. Now, let's say that we know we have 3%, but we would like to come in and let this be a function of time. So if I do that, then I'm going to change this notation to A of t. Is 10,000 plus 0.03 times t. And I can see that I can go 10,000, use the distributive property, and plus 300t, and I can see that A of t equal 300t plus 10,000 starts to take on the form of a linear function. Y equals mx plus b. My slope is 300. My intercept is 10,000. And my y, which is the ending balance after a particular t, can be calculated by using this function. Now, it's going to be kind of cool, something in your calculator that you could do. We can come up to y equal, and we can get rid of that, and we can just type in 300. We can't use t, we're forced to use x, plus 10,000. And we can graph that over the window that we choose. So how many years do we want to go out? Well, let's just say we want to go out 10 years. I'm sorry, that's not good. Start at 0, go out 10 years. And then we have to set our y accordingly. Well, it's kind of sometimes hard to really know how to set your y appropriately. So I'm going to show you guys a trick. All you have to do is just set some y min and some y max, just as long as the y max is bigger than the y min. Now, if you'll come to zoom and go all the way down to the bottom and go zoom fit, what zoom fit does is it sets your window on your calculator to correspond with the x's that you've chosen. It won't change your x's, but it will adjust the y's to give you the best picture based on the x's, and the x's in this case is our time that we've input. So guys, hit enter, and it's going to give us our graph. Now let's go second function, calc. Let's go value after half a year. Look familiar? Let's say we want to see what we'll have after 7 years. Pretty cool. Let's say we want to see what we've got after 15 years. It's not going to work because we didn't set up our calculator to go that far. So guys, if we do want to run out further, it's not a big deal. Just go back to our window and say, well, I'd like to run it out a little bit further, so let's go out to 20. Readjust the y according to the new x's that we've chosen. It graphs it, goes second function calc, value, and now it'll allow us to go 15 years. So you'd have $14,500. So your $10,000 would have grown to $14,500 over 15 years. So you're like, well, I'd like to see what it looks like over 25 years. Well, you know what's going to happen, right? It's not going to work because we didn't go out far enough. So go to window, go out far enough to examine 25 years, hit zoom, readjust your y's, and then you can see that after 25 years, your $10,000 investment at 3% annually, if the interest is compounded linearly, you would have $17,500. So you would have got $7,500 interest on your $10,000 investment. Now, all that is fine and dandy, and it works. You know, linear functions do pop up in mathematics, but in business applications, I should say. But the function that we encounter most in this class looks like this. Has an exponent. Up here, we didn't have the exponent. The exponent was just 1. It was set as 1. That's what made it a linear function. Well, that's not what made it a linear function, but that is a characteristic of a linear function. The exponent is pretty much irrelevant because there is no exponent other than the redundant 1. Okay? But in this situation, we have an exponent that varies. We allow ourselves to put in different n, which I'll explain in just a second, different times. So in this situation, this is still the ending balance. This is still the beginning balance. The rate is still R. T is still years. But this N that we run into is compounds per year. How many times per year do they calculate the interest that I'm earning? Up here, it's just calculated once per year, and then that money goes over in a separate account and does nothing else. When you have a compounding situation, the money, the interest that is actually earned on that particular compounding period is put back into the initial investment and becomes kind of like interest on top of interest. Well, guys, when you're investing money, that's what you want. So to give you an illustration of this, I want to set, just for us to talk, I want to set, talk this through. I want to set n equal 1. So we are calculating on one compound per year. So we call that an annually compounded rate. So n per equal 1. So guys, when that happens, let me readjust my screen there. When that happens, A equal P times 1 plus R over N to the NT becomes n equal 1 becomes and let's go back to the interest rate being 3% as before. Becomes this. We can clean that up. And guys, I'm being sloppy here. Let's set the interest or the initial investment at $10,000, just like I did before. This becomes just 1.03. And then the variable that we have is in the exponent. Now, guys, before when we had the simple interest, the annual interest, notice that the variable t was part of the expression, was part of the 1.03. And we couldn't add those because to be able to add this term and this term, you've got both of them would have to have a t. So we had to leave these separate. But over here, we can't add those because 1 and 0.03 are just numbers. Neither one of them has a variable. Well, guys, this is called an exponential function because our variable t is in the exponent. Now, these things in your calculator are treated just a little differently. Actually, they're treated a lot differently. So if I go to y equals, and I want to come down to and put this in my calculator, I'm going to go 10,000, left parentheses 1.03, and again, I'm trying to keep the same problem here, except the problem we looked at before that's in y1 was a simple interest, and this is compounded. So I want to erase that, and I do that with the, let me get this up there where you can see it. To do to a power, we use this key right here, and I want x to be my variable. Okay. Now I want to go into my window, and I want to just get this back to, let's go 25 years. And I want to come into my y, and again, I just want to set it something 0 and 1. Doesn't matter as long as my y max is bigger than my y min. It doesn't matter what I put here. because I'm going to adjust my Y by using zoom fit to give me the best picture now for both functions. So notice what happens. They start out about the same, but the second function starts building more quickly because it is calculating the interest based on previously earned interest. So it calculates the interest, throws that back into the principal, calculates more interest based on the principal and interest. And once we get into the mathematics of finance, we will break this thing down and look at some really cool things. Now, but right now, I just want to just motivate the reason that we need to study exponential and logarithmic functions in this class. Now, something kind of cool that you can do. I'm not really happy with the clarity of that. Let's see if we can get it a little clearer. That's a little better. Now, what we could do here is we can go out and compare a couple of ways. So I can go second calc and go value. And let's say I want to focus on what it looks like 10 years later. Well, for simple interest, I'm going up with 13,000. All I got to do is hit my up arrow, and I can see that I would end up with about $500 more if I had got compounded interest. Even gets a little bit better as I get on out. Let's go on out to say 20 years. 20 years, if I had simple interest, I'd get 16,000. Hit my up arrow. I see that I get 18,061, almost $2,100 more money by using the compounded interest. So guys, exponential functions are important in studying business relations, business models. And again, the motivation for studying these. Now, something else that just put on the back burner. You got something on your calculator called a table set. So if I go second function table set, I can tell the table where I want to start. The guys, my variable here is years, so I'm going to start at 0, and I'm going to go up. This is just this triangle just means delta, or change in your table values. So with a 1 there, I'm going to go from 0 to 1 year to 2 year to 3 year to 4 year. If I set this at 0.5, I would go from 0 to 6 months to a year to 18 months to 2 years to 2.5 years, and so on and so forth. But I want to just go up by the year. Now, if I come over in my calculator and go to table, that's blue, so I got to hit that key first. I'll get a table of values. Guys, this is simple interest. Notice not much difference at first. In fact, right here, there's only $9 difference. Right here, there's $27 difference. Right here, there's $55 difference. But if we focus on the later years, and come on down into right in here, we can see that, for example, 24 years, there would be over $3,000 difference. Now, what if you're like, well, God, that's kind of cool, but I'd like to see what it looks like 75 years later. I plan on living a long time. What's my investment going to look like 75 years down the road? I don't know about you, but I don't want to sit there and just keep going to 75. So I'd go up here to my table set, start at 75, go back and look at my table. So you can see at the year 75, if you did leave this investment in there for 75 years, compounded, you'd have almost $92,000. Simple interest, you'd have $32,500. So the difference becomes more significant the further out that you get. So, guys, that's the motivation for solving for studying exponential functions. If you need a motivation, if not, just say, hey, we're studying them because Darbro thinks they're the greatest thing since sliced bread. Actually, I don't, but I don't know. Maybe that would make you feel better. All right, guys, what's an exponential function? an exponential function for the most part uh, is f of x equal b raised to the x power, where b is greater than 0, and it would be kind of redundant to look at b equal 1. If we put a 1 in for b, and guys, by the way, b equals what we call the base. If we put a 1 in there, well, 1 raised to the second power is 1, 1 raised to the third power is 1, 1 raised to the fourth power is 1, 1 raised to, okay, I'll stop. You get the hint. It'd be a constant function, just a line at 1. So that's not exponential, but anything greater than b, greater than 0, does give us. Okay? Now, couple of characteristics of this function. First thing, all will pass through the point 0, 1. Let's think about that. Choose any base. I'm going to choose 8. What is f of 0? 1. Any number raised to the 0 power is 1. So when x equals 0, then y will be equal to 1. That is all that is saying. Second characteristics. Continuous curves. Not broken. So you're not going to get into something like that. That'd be pretty cool if you could see that, wouldn't it? You're not going to get anything like that. These things are continuous curves. These things being exponential functions. Most important thing, b greater than 1. We have an increasing function. And when b is from 0 to 1, we have a decreasing function. Now, what do I mean by that? What's going on with this increasing, decreasing stuff? Well, let's just choose a base of 3. Well, clearly, in this case, our base is greater than 1, right? So from what I told you before, this should be an increasing function. Well, let's take a look at some x's and some y's. For the function y equal 3 raised to the x power, or if we're using function notation, f of x equal 3 raised to the x power. So I can look at some values. Well, from what I said before, when x is equal to 0, we know it must contain the point 0, 1. When I put 1 in here, I know I get 3. When I put 2 in, I get 3 squared, which is 9. And when I put 3 in for x, I get 3 cubed, which is 27. Clearly increasing. But what if b is equal to 1/3? Well, then I get a situation where my b is between 0 and 1. So my function or if we want function notation, which I prefer, f of x equal 1/3 to the x power. And I'm going to do my x's and y's horizontally here just because I'm running out of room. but I can still go 0, 1, 2, and 3 as my values. Well, regardless, when I have x equals 0 and I put it into either one of these, I get 1/3 to the 0 power, which is just 1, again, passing through the point 0, 1. I put 1 in, I get 1/3 to the 1 power. Put 2 in, I get 1/3 times 1/3. Put 3 in, I get 1/3 times 1/3 times 1/3. And I get decreasing. Now, this is really easy to see on our calculator. Instead of all the fancy smancy stuff, let's put in just 3 raised to the x power. And let's put in 1/3 raised to the x power. Just like before, let's see what the window is. Let's just run our x's from 0 to 3 like we did before. Y's, put in something, it doesn't matter, just as long as the y max is bigger than the y min. Hit zoom, fit, and we will get our functions. The first function is going to be the 3 to the x. You'll see it's increasing. The next function is going to be 1/3 x. You can see that it is decreasing. Now, what actually happens with this function, the second one, is it starts up here and actually comes down like this. Okay. All right. Well, I didn't say that correctly. I said starts up here. I meant, well, I'll tell you what. Let me show you what I mean by that. Let's go for -3, and let's go zoom fit. All right, this will be better. I didn't point far enough over because. Okay, there's the y equal 3 to the x, and there's y equal 1/3 to the x. So it comes down, but I needed to go over here to show you that it comes like this. So it's a decreasing function. The domain here is all numbers, all reals. We can put negative numbers in for x. But the range, the y's that these functions can attain has to be above y equals 0. So our range would be y values above 0, not including 0. All right, guys, I think actually we're in pretty good shape to go on to the tougher stuff. Logarithms are tougher. They're harder than exponential functions. So let's go ahead and shut this video off, clear it out, get rid of it, get it behind you, and that way we'll have time for logarithmic functions. So next up, logarithmic functions. All right, gang, have a good one.